details, and so they should be made clear or clearer. That's my main and growing criticism of Sipser. I mean, all relationships are a compromise, right? Similarly with all textbooks. There's virtually no perfect textbook. I mean, some get pretty good and they become classics. Well, Sipser's book has become pretty much of a classic, but still, it's let's say at the low end of the classics, I would say, because he could be clearer. That's my main criticism. But still, it's pretty good. You can see the logical progression of the material. You can see why he's chosen to discuss a particular point or topic at a particular stage in the development of the text. And you can see it's well structured. So in that sense, it's quite impressive. It's just he's not, well, in my view, not thorough enough with the details. And maybe that's the difference between pure mathematicians on the one hand and physicists and computer scientists on the other. They're looser and a bit sloppier with the fine points. And the mathematicians, they like precision. They want things to be clear. They don't like ambiguities and so on. They don't like messiness. Right. Okay, so what happens when you don't have epsilons here? What's going on? Well, maybe it'd be easier to explain that because you can have a mix, right? You can have you may have all of these non-epsilons. You may have just one of them is an epsilon. You have two of them as an epsilon. All three of them as an epsilon. You can have all possibilities, okay? And each one has its own interpretation. Now, this is what I mean by details, right? But you need, here's what I was figuring out last night, trying to understand just how this transition diagram worked. Why did it work? Why does this transition diagram implement, or why does it function as a PDA? Why does it recognize this particular language? Trying to figure out. And the details are in these labels, right? Well, of course, the choice of the four states, why four states. Well, I'll explain it. But a lot of the detail is in the labels. So I'll sort of go through it, and I'll give you several walkthroughs with particular inputs, starting at the empty string input, and then 0, and then 1, a bit systematically, and then 0, 1, and then 1, 0, and then 1, 1, and probably 1, 1, 0, 0, because that'll work. Oh, sorry, 0, 0, 1, 1, that'll work. Okay, and hopefully by then you'll get the idea. And you need to get the idea, because there's two more examples of this kind of thing, and then later on the board we'll start proving the equivalence of PDAs, non-deterministic PDAs, and context-free grammars, CFGs. And you'll need an understanding of how this works for that as well. So it's important. Things are getting a little tougher. That's to be expected. Right? That's why I said it's a mix of senior and master level text. All right. Well, let me. So here we've got what, 2 out of 3 with epsilons. Here's 1. Here we've got 2, 1, 1. So what's going on now? Just quickly summarising. If you've got an epsilon here, ignore the input string. Okay, just do nothing. Don't read it. Just ignore it. And here, if the second one, the B position here, like here, 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 and so on, B position. If that's an epsilon, then ignore the stack. Don't do anything with the stack. Just leave it as it is. And if the epsilon here, if there's an epsilon here in the C position, ignore the stack. But in the sense, here would be don't read pop and here it would be don't write. In other words, don't push. Okay? Remember when you push a stack, you put a new element, a new symbol on the top of the stack, and all the other elements, all the other symbols already there, assuming one symbol per position in the stack, all those other previous symbols get pushed down one. Okay, that's pushing. And when you re-pop the top one, you read what the top one is, and pop it, then all the symbols below it pop up one. They all move up one position. So what was the second top symbol becomes the top symbol. Okay. All right. Now let's try and figure out what's going on here. Now remember, there's no explicit mechanism in a PDA to detect when a stack is empty. Right? So you need a trick, and the trick was to use the dollar sign. So the very first thing you do is push a dollar sign. You put a dollar sign onto the stack. So then the contents of your stack then is now just dollar, at the top position. That's it. And why do you do that? Well, because later when you're pushing other things, so the dollar will get progressively pushed down, 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 down. And then when you pop, 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 the dollar sign will come up. And when you actually can read the dollar sign, well then you obviously know the stack is empty. I mean, it's not strictly empty because you still have the dollar sign in it, right? But effectively it's empty. All the other things other than the dollar have gone, right? So effectively your stack is empty. So that it's a trick. Okay. So the first thing you have to do is push the dollar sign, and that's what this is doing. Right? Now you start. Now this is your start state, right? Here's your start state arrow indicator. Okay. Now why is it double circle? In other words, why is this Q1 an accept state? Well, you could have as input, your input string could be the empty string, right? And that satisfies this, because n here would be what, 0 and 0. So there are there are no zeros and there are no ones. That's the empty string. So that the empty string satisfies that. Right? So the empty string is a member of this language. So if there's nothing in the input string, that should be a member of the language. It should be accepted. Okay. Well, it can't transition. It can't read anything. So it just stays in Q1, and that's an accept state. So you need to make Q1 an accept state, right? So you put a double ring around it. Okay, now assume now that the input string is not empty. So the input string is not epsilon. Okay. Well, and the first thing we want to do, and we're talking about a PDA, right? This is the transition diagram for a PDA. So the first thing we want to do is to push a dollar onto the stack, because we need that to show us when the stack is effectively empty later. We'll need that dollar. All right. Well, have a look what's going on here. Ignore the input string. Ignore the stack, and then what's on the right hand side? That whatever this symbol is, unless it's epsilon, whatever that symbol is, push it. Okay. All right. So you're ignoring the input string, you're ignoring the stack, what's currently on the top of the stack, you're ignoring that, you don't care. And because at the beginning it'll be, we just started, it'll be empty anyway, right? So, and what's on the right hand side, if it's not epsilon, push that symbol that's on the right hand side. Okay, so you're pushing dollar. So now you've got dollar on the stack. It's on the top level of the stack, and that's it. All right. Okay. Now let's. What do we? Well, let's start going through it. So we're now and you transition to with the transition rules, substitution rule. No, transition rules. No, substitution rules. That's with a grammar, right? We're talking about PDA now. So we're talking transition rules, transitions from state to state. Whereas substitution rules, they're concerned with strings, substituting variables for other things. Okay, so let's do it systematically now. So we've done the case that the input string is empty. Now let's say the input string is a single 0. That's it. Okay. So we we push the $, so we're now in state Q2. We read